So Cartesian geometry, a couple of formulas which we should be familiar with. First of all, our distance formula, there it is in all its glory. A couple of things not to get hung up about. Some people say, oh look, x2 goes first, so therefore y2 has to go first. Well, it doesn't actually in this formula because we're squaring anyway, so it doesn't actually matter which way round. It's really just saying the difference in the x values squared plus the difference in the y values squared. So I want to find the distance between these 2 points, sub it in, and there we go. Simplifying the third down, we get 2 root 5. Essentially all we're doing is Pythagoras' theorem. Because you've got 2 points on the plane, you could join them up, but then you could create a right-angled triangle. One side would be the difference in the x values, the other side the difference in the y values. I guess the other one we see a lot of is our midpoint formula, which looks something like that. And again, the order doesn't matter because you can add in any order. So I found the midpoint, substitute in, and there is. And essentially what we're doing there is finding the average of the x values and the y values, because the average is one of those measures of the centre. So middle point, we're finding the centre of 2 points. So there's Euclidean geometry, Cartesian geometry, but they're all geometry and they are interchangeable, and we can use Euclidean geometry ideas in Cartesian geometry and vice versa. So all those theorems we know in Euclidean geometry can help us. Let's have a look at quadrilaterals then and how we classify them. Now any quadrilateral, or any shape for that matter, can be classified by the different features that they possess. And as you branch down our family tree of quadrilaterals there, they become more specialised in their features. So any feature I know about a particular shape, when I branch down, that new shape still has all those features, I guess is what we're saying. So for example, the rhombus there, it would have all the same properties as a parallelogram, a trapezium, a kite, a quadrilateral, as well as it has some of its own special features as well. Let's branch down the tree. Quadrilateral, pretty boring really. Oh, it's got 4 sides, we know that. How useful is that? Oh, it's got 4 angles as well. Yeah, terrific. But other than that, really, no specific properties other than we're talking about a 4-sided object. But then we start branching down, and we'll go over here to the kite. What do we know about the kite? We have adjacent sides are equal. Well, probably a better way of saying that is a pair of adjacent sides are equal. Otherwise, that kind of implies all the sides are equal. But we just say, okay, there'll be pairs that are equal. But the other interesting thing is the diagonals in the kite will always be perpendicular to each other. There is a formula for the area of a kite. You might look at that and say, hang on, isn't that the formula for the area of a rhombus? Actually, no, it's the formula for the area of a kite. It's just the fact that a rhombus is a kite, therefore you can use that formula. I could also branch from the quadrilateral and get a trapezium. What do we know about that one? It has 1 pair of parallel sides. We have an area formula for that as well. Half the perpendicular height, the distance between the parallel sides, times the sum of the 2 parallel sides. The trapezium can branch down to the parallelogram, where we now have 2 pairs of parallel sides. So I guess what that means is you could use the formula for the area of a trapezium to find the area of a parallelogram. But we also now know that the opposite sides in the parallelogram are going to be equal, but also the opposite angles in the parallelogram will become equal as well. As far as the diagonals go, they'll bisect each other. And we do have a formula for the parallelogram. We normally just say base times height, where height is the perpendicular distance between any two parallel sides. If you want to show something is a type of shape, then we would have to show one of these features. But with the parallelogram, actually, we can combine 2 of them together and only prove it for 1 pair of sides. So if you've got a pair of sides and you know they're both equal and parallel, it must create a parallelogram. So kite, parallelogram. Parallelogram branches down to then a rectangle. We become a little bit more specialised because now we know that those angles are actually 90 degrees. It also now makes the diagonals equal in the rectangle. Length times breadth, there's an area. Our rhombus, which is both a kite and a parallelogram. So it joins those features together, but it now also has this additional feature of the diagonals will bisect the vertex. And then we finally branch down to, I guess, the perfect quadrilateral, the square. It has all the properties of all of the different quadrilaterals. It has a formula for the area. There it is, s squared, hence the name of the shape. Which came first, the shape or the name of the power? I wonder. Was it the square? Or the square? But anyway, the area is the side squared. Okay. Yeah, I think it was probably the shape first. So we've got this picture. We want to show it's a rhombus. All right. We know the coordinates of the vertex show it's a rhombus. We need to show the features of a rhombus. So what did I do? I'm having a look at the diagonals. Let's find where they meet. So I found the midpoint of AC, and then I found the midpoint of BD, and they're the same. That tells me the diagonals are bisecting each other. Well, that's not good enough to say it's a rhombus, but it is good enough to say it's a parallelogram. So I know it's a parallelogram, there's my reason. I know the diagonals bisect each other. Okay, let's actually look at the sides then, but I don't need to look at all the sides, I just need to find a pair of adjacent sides that are equal. So I picked CD, I found its length is 5. Now I'll pick AD, it's also 5. Brilliant. It's a rhombus, but I've got a rhombus with adjacent sides being equal. That's just one way I could have done it. I mean, I could have done it by finding the length of all 4 sides and said, oh look, all 4 sides are equal, therefore it's a rhombus. How else could I have done it? I could have shown the opposite sides were parallel, making it a parallelogram, and then go from there. However you choose to do it. Okay, so there's a brief little start into our Cartesian geometry.